Welcome to our exploration of variational autoencoders or VAEs. Before diving into the complex architecture, we need to understand the fundamental concept that VAEs address, modeling probability distributions. Let's start with the data distribution represented mathematically as Px. What does this mean? Imagine we have a collection of cat images. The distribution Px describes how likely it is to observe each possible cat image in the real world. If we visualize this distribution as shown on our screen, we can see it as a curve where the height at any point represents how likely that particular cat image is to occur naturally. The dots you see are actual samples from this distribution. These are our training examples. This distribution is incredibly complex. For example, a 64 times 64 pixel color image has over 12,000 dimensions. Real-world data like cat images occupy only a tiny structured region within this vast space. Most random configurations of pixels don't look like cats at all. Our goal in generative modeling is to learn this complex distribution Px so that we can generate new cat images that look realistic. The challenge is, how do we model and learn such a complex, high-dimensional distribution from a limited set of examples? Traditional methods struggle with this problem, which is why we need more sophisticated approaches like variational autoencoders. Why is directly modeling Px so difficult? There are several fundamental challenges that make this problem particularly hard. First, real data lives in an extremely high-dimensional space. As I mentioned earlier, even a modest 64 times 64 color image has over 12,000 dimensions. The number of possible configurations grows exponentially with the number of dimensions, creating what's known as the curse of dimensionality. Second, real data distributions are incredibly complex. They're not simple shapes like Gaussians. They have multiple modes, intricate correlations between dimensions, and sharp boundaries between valid and invalid examples. For instance, the space of valid cat images has a very complicated structure changing. A few pixels might turn a realistic cat into something that doesn't look like a cat at all. Third, we typically have a limited number of samples. While we might have thousands of cat images, that's still infinitesimally small compared to the size of the space we're trying to model. Imagine trying to understand the shape of an entire mountain range by visiting just a few locations. These challenges make directly modeling Px essentially intractable for complex data like images. We need a more clever approach on that can capture the structure of our data more efficiently. This is where latent variable models come in. Instead of directly modeling the complex distribution in the high dimensional space, what if we could find a simpler, lower dimensional representation? That's the key insight that leads us to variational autoencoders, which we'll explore next. Latent variables are hidden factors that we believe generate our observed data. They represent the underlying structure or features that aren't directly observed but help explain the patterns we see in our data. For our cat examples, latent variables might represent meaningful features like fur color, eye color, ear shape, face width, and so on. These features are latent because they're not explicitly labeled in our dataset. We just have pixel values, but they're the underlying factors that create the variety of cats we observe. The crucial insight is that while the space of cat images is incredibly complex and high dimensional, the space of these underlying features might be much simpler and lower dimensional. Perhaps we only need 20 to 50 volts variables to capture most of the variation we see in cat images, rather than the thousands of dimensions in the pixel space. In mathematical terms, we are introducing a prior distribution over these latent variables, P of Z, and a conditional distribution P of X given Z that describes how to generate an image X given a specific set of latent features Z. This lets us express the overall data distribution as P of X equals the integral of P of X given Z times P of Z with respect to Z. This integral sums up all the different ways to generate an image X by marginalizing or integrating over all possible latent variables Z, weighted by their probability. In other words, we are combining the probabilities of all the different latent factors that could have generated our observed data. By introducing these latent variables, we've reformulated our problem in a way that might be more tractable. However, this approach introduces new challenges that we'll explore next. While introducing latent variables gives us a promising direction, we've run into a new problem. The integral P of X equals the integral of P of X given Z times P of Z with respect to Z is typically intractable. Let me explain why this is a significant challenge. First, what does intractable mean in this context? It means we can't compute this integral exactly in a reasonable amount of time. The space of possible z values is too vast, and the relationship between z and x is too complex. Let's understand why using a cat example. If we imagine each latent variable represents a feature like fur color or ear shape, we would need to sum over all possible combinations of these features, weighted by how likely each combination is, and then calculate how likely each combination is to produce our specific cat image. This involves computing p of x given z, the probability of generating a specific cat image given particular latent features for every possible value of z, and then integrating over all these values. For continuous latent variables, that's an infinite number of calculations. An equally important problem arises when we want to go in the reverse direction, inferring the latent variable z that likely generated a specific image x. This requires computing the posterior distribution p of z given x. Using Bayes' rule, we get p of z given x equals p of x given z times p of z divided by p of x. But this requires computing p of x, which brings us back to our intractable integral. We are caught in a circular problem. The red x you see in our diagram emphasizes that we can't compute this integral directly. We need a clever workaround, a way to approximate these distributions without having to compute the intractable integral. This brings us to the key innovation of variational autoencoders, using variational inference to approximate the posterior distribution, which we'll explore in the next screen. Before we dive into variational inference, let's make sure we understand what the posterior distribution p of z given x really means in the context of our cat examples. The posterior distribution p of z given x answers the question, given a specific cat image x, what latent features z likely created it? For instance, if we observe a Siamese cat with blue eyes, the posterior distribution would tell us the probability of different latent variable values that could have generated this particular cat. It might tell us that fur color is very likely to be a specific shade of brown, eye color is very likely to be blue, ear shape is likely pointed, and so on. As you can see in the visualization, for each feature like fur color, eye color, size, and ear shape, the posterior gives us a probability distribution. Some values are more likely than others for the specific cat. This distribution is incredibly useful because if we could compute it, we would understand the underlying features of our data. We could potentially manipulate these features to generate new controlled variations. But as we learned in the previous screen, computing this posterior exactly requires evaluating an intractable integral. Mathematically, we need p of z given x equals p of x given z times p of z divided by p of x. But p of x is precisely the integral we can't compute. This is the fundamental challenge that variational autoencoders address, approximating this posterior distribution without having to compute the intractable integral. In the next screen, we'll explore how neural networks can help us implement a variational approach to this problem. Now let's see how neural networks help us implement variational inference in practice. We need to approximate two key probability distributions, the posterior distribution q of z given x and the likelihood p of x given z. First, let's look at the encoder network. This neural network takes a cat image x as input and outputs parameters for our approximate posterior q of z given x. Specifically, for each latent feature, it outputs a mean mu and a variance sigma squared, defining a Gaussian distribution. For example, when we feed a Siamese cat image to the encoder, it might output values suggesting that the fur color feature has a mean of 0.7 leaning towards Siamese brown with a small variance of 0.1, meaning it's quite certain. For eye color, it might output a different mean and variance. The beauty of this approach is that we are not trying to define these distributions manually. The neural network learns the appropriate distributions by training on many examples. Next, the decoder network performs the reverse process. It takes a latent vector z as input and learns to reconstruct the original cat image Mathematically, it implements the likelihood P of x given z, the probability of generating a particular cat image given specific latent features. When we feed a latent vector with certain values for fur color, eye color, etc., the decoder generates a cat image with those characteristics. During training, it learns to reconstruct images that match the original input as closely as possible. There's one more critical component, the reparameterization trick. Why do we need this? Neural networks are trained using backpropagation, which requires operations to be differentiable. However, sampling from a probability distribution is not differentiable. We can't compute how a small change in the distribution parameters affects a random sample. The reparameterization trick solves this by reformulating the sampling process. Z equals mu plus sigma element y is multiplied by epsilon, where epsilon is a random sample from a standard normal distribution n of 0, 1, and element y's multiplication represents multiplying corresponding elements together. This separates the randomness epsilon from the parameters we're learning mu and sigma, allowing gradients to flow through the network during training. These neural networks give us the tools to implement variational inference in practice, which we'll put together in the full VAE architecture next. Having established how neural networks can help us implement variational inference, we now need to determine what objective function to optimize during training. This brings us to the evidence lower bound, or ELBO. The ideal objective would be to maximize the log probability of our training data, log P of x, for each cat image x. This would mean finding model parameters that make our observed data as likely as possible. However, as we've seen, computing P of x directly is intractable. In step 1, we start with the expression for log P of x as log of the integral of P of x given z times P of z with respect to z. This is the log of the integral we previously established was intractable. Here we can visualize the problem. We have a cat image x and we want to maximize its log probability log P of x. This involves summing over all possible latent representations z in the latent space. In step 2, we introduce a mathematical trick. We multiply the expression inside the integral by q of z given x divided by q of z given x, which equals 1 and therefore doesn't change the value. This gives us log P of x equals log of the integral of P of x given z times P of z times q of z given x divided by q of z given x with respect to z. Why do this? It may seem like an unnecessary complication, but this step is crucial because it lets us introduce our approximation q of z given x into the equation. Instead of working directly with the intractable posterior, P of z given x will work with our approximation q of z given x that we can compute using our encoder neural network. This mathematical trick is our first step towards deriving the LBO, which will give us a tractable objective function for training our VAE. In the next screen, we'll continue the derivation and arrive at the final elbow objective. Continuing our derivation of the elbow, let's pick up where we left off. We had rewritten log P of x as log P of x equals log of the integral of P of x given z times P of z times q of z given x divided by q of z given x with respect to z. In step 3, we recognize that this can be rewritten as the expectation with respect to our approximation q of z given x. Log P of x equals log of the expectation with respect to q of z given x of P of x given z times P of z divided by q of z given x. What does this mean intuitively? We're averaging the ratio P of x given z times P of z divided by q of z given x over different values of z, where these values are drawn according to our approximation q of z given x. For our cat example, this means we are averaging over different possible latent representations of our cat image, weighted by how likely each representation is according to our encoder model. Now comes the crucial step. In step 4, we apply Jensen's inequality, which tells us that the log of an expectation is greater than or equal to the expectation of a log. Log of expectation of x is greater than or equal to expectation of log of x. This gives us log P of x is greater than or equal to the expectation with respect to q of z given x of log of p of x given z times p of z divided by q of z given x. The inequality is illustrated with our CAD diagrams. Log of average is greater than or equal to average of log. This is Jensen's inequality, a fundamental result in mathematics that holds because the logarithm is a concave function. Why is this important? Because the right hand side is something we can compute. It's an expectation that we can approximate by sampling from q of z given x, which is exactly what our encoder network allows us to do. This expression is our evidence lower bound, or ELBO. It's a lower bound on log p of x, meaning that if we maximize this lower bound, we're also pushing up the true log probability of our data. The ELBO gives us a tractable objective function that we can optimize during training. In the next screen, we'll further expand this LBO to reveal its interesting components and understand what it's really optimizing. Let's expand our elbow further to gain deeper insights into what it's actually optimizing. We left off with log p of x is greater than or equal to the expectation with respect to q of z given x of log of p of x given z times p of z divided by q of z given x. In step 5, we use the logarithm property log of a times b equals log of a plus log of b to expand this expression. Log p of x is greater than or equal to the expectation with respect to q of z given x of log p of x given z plus the expectation with respect to q of z given x of log of p of z divided by q of z given x. This separates our objective into two distinct terms, each with its own interpretation. In step 6, we recognize that the second term is the negative of the Kullback-Leibler KL, KL divergence between q of z given x and p of z. Log p of x is greater than or equal to the expectation with respect to q of z given x of log p of x given z minus the KL divergence between q of z given x and p of z. But what is KL divergence? It's a measure of how different two probability distributions are from each other. In our case, it measures how much our approximation q of z given x differs from the prior p of z. We can visualize this. Q of z given x is our approximation of the posterior for a specific cat image, while p of z is our prior distribution over latent variables, typically a standard normal distribution. The KL divergence measures the gap between these two distributions. So our ELB objective has two terms. Reconstruction term expectation with respect to q of z given x of log p of x given z. This encourages the model to reconstruct the input data accurately. KL regularization term, negative KL divergence between q of z given x and p of z. This encourages the approximate posterior to be close to the prior. This dual objective is what makes VAE so powerful. The reconstruction term ensures the model captures the data well, while the KL term acts as a regularizer, preventing the model from overfitting and ensuring the latent space has good properties for generation. Now that we have a clear objective function, we are ready to put all these pieces together into the complete VAE architecture and training procedure. Now that we understand the mathematical foundations, let's explore how neural networks fit into our variational inference framework. How do we actually implement these complex mathematical concepts in practice? First, let's look at the encoder network. This neural network is responsible for approximating q of z given x, that is our approximate posterior distribution. Looking at a diagram, we start with our input cat image on the left. This image gets fed into the encoder neural network, which processes the pixels and extracts meaningful patterns. The encoder's job is to output the parameters for our approximate posterior distribution q of z given x. For each cat image, it predicts a mean, mu, and variance sigma squared that define a Gaussian distribution in latent space. Essentially, the encoder is telling us, given this specific cat image, here's my best guess about what latent features might have generated it and how confident I am about each feature. For example, when processing a Siamese cat image, the encoder might output values suggesting that the fur color feature has a mean of 0.7, indicating Siamese brown with a small variance of 0.1, meaning it's quite certain about this. For eye color, it might predict different parameters. The beauty of using a neural network here is that we don't need to manually define these mappings. The network learns them from data through training. Next, let's examine the decoder network. This network implements the likelihood P of x given Z, the probability of generating a particular cat image given specific latent features. The decoder takes a latent vector Z as input and learns to reconstruct the original cat image. When we feed a latent vector with certain values for fur color, eye color, and other features, the decoder generates a cat image with those characteristics. During training, it learns to produce images that match the original input as closely as possible. Finally, we need to address an important technical challenge, the reparameterization trick. Why do we need this? Neural networks are trained using backpropagation, which requires operations to be differentiable. However, randomly sampling from a probability distribution is not differentiable. We can't compute how small changes in the distribution parameters would affect a random sample. The reparameterization trick solves this by reformulating the sampling process as z equals mu plus sigma times epsilon, where epsilon is a random sample from a standard normal distribution n0, 1, and the multiplication is element-wise. This separates the randomness epsilon from the parameters we're learning mu and sigma, allowing gradients to flow through the network during training. This trick is essential because it enables us to backpropagate through the sampling operation, which is necessary for training our encoder to predict good distribution parameters. With these neural network components and the reparameterization trick, we now have all the building blocks needed to implement variational inference in practice. In the next screen, we'll see how these components fit together in the complete variational autoencoder architecture. Now let's put everything we've learned together to understand the complete variational autoencoder architecture and how it's trained. The VAE workflow starts with an input cat image, X. This image is fed into the encoder neural network, which outputs the parameters for our approximate posterior distribution Q of Z given X. Specifically, the mean mu and variance sigma squared for each dimension of our latent space. Next comes the reparameterization trick we discussed earlier. Z equals mu plus sigma element y is multiplied by epsilon, where epsilon is sampled from a standard normal distribution n of 0, 1. This allows us to sample from our approximate posterior while keeping the operation differentiable. This gives us a latent vector Z, which captures the essential features of our cat like fur color, eye color, etc. This vector is then fed into the decoder neural network, which generates a reconstructed cat image, x hat. The decoder learns to implement the likelihood P of x given Z. During training, we optimize the elbow objective we derived L of theta, phi equals negative expectation of log P theta of x given Z plus scale divergence between Q phi of Z given x and P of Z, where theta represents the decoder parameters and phi represents the encoder parameters. This loss function has two distinct terms. One, reconstruction loss, negative expectation of log p theta of x given z. This term encourages the decoder to accurately reconstruct the input cat image. In simple terms, it says make the output cat look like the input cat. 2. KL regularization, KL divergence between Q phi of Z given X and P of Z. This term encourages the approximate posterior to be close to the prior, usually a standard normal distribution. It essentially says keep the latent space well behaved. The balance between these two terms is crucial. Too much weight on reconstruction and the latent space might not be well structured for generation. Too much weight on KL regularization and the reconstructions might be poor. Once we've trained the VAE, we can use it in several exciting ways. We can generate new cat images by sampling from the prior P of Z and running the samples through the decoder. We can interpolate between cats by moving smoothly in the latent space. We can even manipulate specific cat features by changing particular dimensions of the latent vector. In the next screens, we'll explore these generation capabilities in more detail. Once we've trained our VAE, we can use it in several creative ways to generate new cat images. Let's explore three key methods. First, we can generate entirely new cats from random latent vectors. The process is simple. We sample a random vector z from the prior distribution P of z, which is typically a standard normal distribution n of 0 I. We then pass this vector through our trained decoder network, which outputs a brand new cat image. The fascinating thing about this approach is that we are generating cats that weren't in our training data. The VAE has learned the underlying structure of cat images, so it can generate new variations that look realistic. For example, here we've generated a black cat with green eyes that never existed in our dataset. Second, we can interpolate between cats in the latent space. If we have two cat images like this brown cat with blue eyes and this black cat with green eyes, we can encode them to get their respective latent representations Z1 and Z2. Then we can create a series of new latent vectors by interpolating between these points. Z equals 1 minus t times Z1 plus t times Z2, where t varies from 0 to 1. As we move t from 0 to 1, we get a smooth transition from the first cat to the second. At t equals 0.25, we see a cat that's mostly brown but starting to get darker with eyes shifting from blue toward green. At t equals 0.5, we get a balanced mix, a medium brown gray cat with bluish green eyes. At t equals 0.75, we're closer to the black cat, but with still some influence from the brown cat. This smooth interpolation shows that the VAE has learned a meaningful latent space where similar cats are close to each other, and the space between valid cat images also contains valid cat images. Third, we can manipulate specific cat features by adjusting particular dimensions of the latent vector. After training, we might discover that certain dimensions control specific features, perhaps Z3 controls eye color and Z7 controls fur pattern. Once we've identified these meaningful dimensions, we can generate cats with specific desired features by adjusting those dimensions. Want a cat with green eyes but orange fur? We can create that by setting the right values in our latent vector. These generation capabilities showcase the power of VAEs as generative models. They don't just memorize the training data, they learn the underlying structure that allows creative generation of new examples. We've come a long way in understanding variational autoencoders. Let's summarize what we've learned and explore some real-world applications of this powerful technology. VAEs use variational inference to learn complex data distributions by approximating the intractable posterior with a simpler distribution parameterized by a neural network. The ELBO objective provides a tractable training target that balances reconstruction quality with regularization. The reparameterization trick enables gradient-based training by making the sampling process differentiable, and the resulting latent space enables powerful generation and interpolation capabilities. Beyond our cat examples, Virginia S have numerous real-world applications across different domains. In image generation, Virginia S are used to create new faces, artwork, and designs. Medical researchers use them to generate synthetic medical images for training data augmentation. Product designers use them to explore new design possibilities by manipulating the latent space of existing products. For anomaly detection, Virginia S excel at identifying manufacturing defects by learning the distribution of normal products and flagging anything that doesn't fit that distribution. They're also used in fraud detection systems and network intrusion detection, where they can identify unusual patterns that might indicate fraudulent activity or security breaches. In data compression, Virginia S provide a way to compress images by encoding them in a lower dimension latent space. They're also useful for creating document embeddings that capture semantic meaning and for extracting meaningful features from complex data. One of the most exciting applications is in drug discovery, where VAs can generate new molecular structures with desired properties. Researchers use them to navigate the vast chemical space generate candidate molecules, and predict drug properties without expensive lab testing. VAEs are a powerful foundation for generative modeling, and they've paved the way for more advanced models like VAE GANs and the recent diffusion models that have revolutionized image generation. Thank you for joining me on this journey through variational autoencoders. By mastering these concepts, you now understand one of the cornerstone techniques in modern generative AI,